An arithmetic sequence, which is also known as an arithmetic progression, is a sequence in which each term after the first term differs from the term preceding it, which means the term that comes right before it, by a fixed constant called the common difference. As a quick example, the sequence 2, 5, 8, 11, 14, etc. is an arithmetic sequence given that each term after the first term, which is 2, is obtained by adding 3 to the previous term. Note that 5, for example, which is the second term, is 2 plus 3, which is basically the first term plus 3. The third term, which is 8, is 5 plus 3, which is basically the second term plus 3, etc. This pattern, of course, continues forever, unless it's a finite sequence and we only want to go to a certain number of terms. The common difference, usually denoted using the letter D here, of course, as we mentioned, is 3, and it can easily be obtained by subtracting any term in this sequence from the term right before it. So the most general way of expressing that fact is to say that D equals an plus 1 minus an for any n greater than or equal to 1. And of course, an plus 1 is the n plus first term, and an is the nth term. All right, so for this first example, we're going to find the common difference for this arithmetic sequence. On this side, you're going to see me create this toolbox that's going to keep expanding as we learn new facts. Right now, we know that we can find the common difference by subtracting any pair of consecutive terms. So for example, here, if I take these two, for instance, makes no difference. I'm going to use negatives just so you get comfortable with that, but I'll show you you don't have to. If I just take this term, -7, and subtract from it the term right before it, which is preceding it, so -14, I end up with -7. Because of these two negatives, I end up with a +14, so -7 +14, so the common difference is 7. Now, I chose these negative numbers because I wanted you to realize it makes no difference what kind of a pair you pick. But of course, if we were just going to do this in our heads quickly, we would have just used these two, for instance. That would be the easiest pair to use. So you would get the same thing. So you would start with 7 and subtract from it the term that comes right before it, which is 0. And of course, you end up with the same common difference. Okay, for our next example, we're going to find the first 4 terms of an arithmetic sequence for which a1, which as you know is the first term, is 2. So we start with a1 equals 2. And we're going to use the common difference of -4. So to get my second term, I'm going to start with my first term and add to it the common difference. Sometimes people get confused because they think, oh, the common difference is going to be positive. Not at all. We just said it has to be the same number that's added to each term to get the next term. So it doesn't mean that it has to necessarily be a positive number. So we end up with -2 for the second term. For the third term, of course, I do the difference here in order to find the common difference, but once I find it, I know that I can take any term and add that to it to get the next term, right? So like once we know that for this sequence that we saw before, that the common difference is 3 by going 11 minus 8, for example, or 5 minus 2, or 8 minus 5, any of those will give you 3. So now if I know, for example, 8 is one of the terms and I want the next term, I add the 3 to get the next term, right? So here I want a3, so I know that the previous term a2 was -2, so I know that I need to add the common difference of negative 4 to that to get my next term. So it'll be negative 6, right? And for the fourth term, which is the last term I'm looking for, I'm going to take the third term, which is negative 6, and add to it the common difference, which is negative 4, and we end up with negative 10. So the first four terms of this sequence are 2, negative 2, negative 6, and negative 10, just like that. Okay, for this next one, we're going to find the first 5 terms of an arithmetic sequence for which the first term is 15 plus radical 5 and the second one is 15. I think you should be able to handle that, so why don't you pause and try it before you come back. All right, remember that we can find the common difference by subtracting any pair of consecutive terms. So here we have a pair, the first and the second. So I can get D by simply doing A2 minus A1, right? So I get 15, which is A2, minus, I'm going to need parentheses because I need to distribute the minus into the first term, which is 15 plus radical 5. So now I get 15 minus 15 minus radical 5. And the 15s cancel out, so we get negative radical 5 for the value of the common difference, D. So now that I know that, all I have to do is add that to the second term to get the third term. So in other words, A3 is going to be A2 plus D, right? So it's going to be 15 plus negative square root of 5, which of course is just 15 minus square root of 5. And then to get the A4, all I got to do is take A3 and add to it the common difference. Now we know A3 is right here, which is 15 minus radical 5. So we're going to add the common difference, which is negative radical 5, to get A4. And we end up with two of these. They can be combined, so we get 15 minus 2 radical 5. Okay? And to get the last one, we're looking for A5. We're going to take A4 and add to it the common difference, right? So we get 15 minus 2 radical 5, which is A4, plus another common difference, which is negative square root of 5. And of course, again, we can combine the radical 5s to get 15 minus 3 radical 5. So the first 5 terms of this sequence are 15 plus radical 5, 15. Those two we already knew. And that the third one is 15 minus radical 5. The fourth one is 15 minus 2 radical 5. And the fifth one is 15 minus 3 radical 5. And there we have the first 5 terms of this particular sequence. Okay, so that's pretty simple. Make sure you can handle it, and then we'll proceed. Next, we want to see how to find the nth term, which is also known as the general term and denoted by an of an arithmetic sequence. Now, if the first term of an arithmetic sequence is a1 and its common difference is d, then notice that a1 is just a1, but if I want a2, I can get a1 and add d to it, right? And if I want a3, I can take a2 and add the common difference to it. But remember, a2 is a1 plus d, right? So I get, if I replace the a2 with a1 plus d, I get a1 plus d. So that's basically a1 plus what? 2d. The next term, a4, is going to be a3 plus d, but we just found that a3 is a1 plus 2d. So I replace a3 with a1 plus 2d, and I get a1 plus 2d plus d, which is a1 plus 3d. let's do one more, which is A5. That becomes A4 plus D. We know what A4 is. It's A1 plus 3D. So we substitute that and we end up with A1 plus 3D plus D. So we get A1 plus 4D. We should be able to see a pattern developing here. Notice that for each term after the first one, it looks like I can get the term by taking A1 and adding 1 less than the term number times the common difference to get my the term of interest. So to get A5, you take A1 and add 1 less than 5, which is what? 4 by the common difference to get A5. And to get A4, we would take A1 and add 1 less than the term number 4, which gives me 3 times the common difference. So if we generalize this for AN, we get A1 plus 1 less than the term number. The term number here is N, so quantity N minus 1 times D, and that will give us the nth term. So this is the expression for the general term, which is, by the way, also how we would describe this particular sequence as a function of n, right? And remember, with sequences, rather than using the functional notation f of n, we use an to indicate what the definition of that particular sequential function is. So any term of any arithmetic sequence can be found as long as we know the first term, A1, and the common difference. And of course, we need to know which term it is we're looking for, so we would need n as well, right? Okay, so here in the next example, we're given a sequence here. We're given a few terms of a sequence. We want to find the 8th term, A8, the n minus first term, An minus 1, and the nth term, as well as the n plus first term, or An plus 1. Notice that our toolbox, in other words, the set of facts we can use is expanding. Now we know that D is equal to An plus 1 minus An, and we know that An can be found using the formula An equals A1 plus quantity n minus 1 times D. So see if you can figure it out and then come back. It's not really that complex, right? All right, as you know, the first thing which we would want to find is D, which we can easily find using this formula right here. So D, I can take any pair of terms. I'll just take the first and the second. So 7 minus 5 will give me 2 for the value of D. Now, for finding any of these 4 terms, the first thing I'm going to focus on is An, because that's my general term. Once I know An, then I can replace n with any other value, such as 8, n minus 1, or n plus 1, and get those results as well. So first I will find An, and I know that I can do that using this formula. So I get An is equal to A1 plus quantity n minus 1D. Let's go ahead and mention the fact that A1 is equal to 5 as well. So we have An equals A1 plus quantity n minus 1 times D. So we get An is equal to 5 instead of A1, and quantity n minus 1 times, I can replace D with 2 because I know that's the common difference. So I'm just going to simplify this. So I get An equals 5 plus distributing the 2 gives me 2n minus 2. Now we can combine the 5 and negative 2. That gives us 3. So we get An equals 2n plus 3. Now you can easily see how this works, for example, for A2, right? A2 would be 2 times 2, which is 4 plus 3, which should give us what? 7, as it does, right? Just a quick check to make sure you haven't made some kind of an arithmetic error, okay? So now that I know an, I can easily find a8. Remember, now we're going to substitute 8 for n in this equation right here. So we get a8 equals 2 times 8 plus 3. So that's 16 plus 3. So that's 19. So there's a8. Now to get an minus 1, that's a little bit more of an abstract question, but it's still important. Remember, I'm going to use the same formula, and I'm going to replace n with n minus 1, right? So I get 2 times quantity n minus 1 plus 3. So I get an minus 1 equals 2n minus 2 plus 3. So I get an minus 1 equals, remember the entire n minus 1 is a subscript, so make sure it doesn't look like you're saying an and then minus 1, meaning 1 less than the nth term. That's not what we mean here. We mean one term before the nth term, right? So we get 2n plus 1, and for an plus 1, in other words, the n plus first term, we're going to take this formula that we have figured out for an, and we're going to replace n with n plus 1. So we get 2 times n plus 1 plus 3. So we get an plus 1 equals 2n plus 2 plus 3. So we end up with, finally, an plus 1 equals 2n plus 5. Just like that. Of course, once we knew the common difference and 2 and the first term 5, we could have found an minus 1 and an plus 1 directly by plugging into there as well. But since this is already a much simpler form of the same thing, it's just easier if we use this particular formula for finding those two values. Okay, so we have found all the ones we were interested in. We have a8, which is 19. We have an minus 1, which is 2n plus 1. And an plus 1, which is 2n plus 5. All right, for our next example, for the given arithmetic sequence, we know that the first term is 8 and the fourth term is -1. We want to find a12 and an. So we are going to find the common difference first, but we're going to do it a little bit differently here because we don't have a pair of consecutive terms that's given to us, but we do know what a4 and a1 are. So let's go ahead and start with our an formula, the general term. We know that's going to be a1 plus quantity n minus 1d, right, as we have here. Now, that means a4 can be written as a4 equals a1, which is 8, plus quantity. Remember, n is 4 for a4, so 4 minus 1d, right? Now, I wrote a4 here because I wanted you to see where all this is going to come from. So I'll just do a new line and I'll substitute what a4 is. It's -1. So I get -1 equals 8 plus, now this is just going to be 3, so 3d. So this is how we will find d, by solving this simple equation. So I get -1 minus 8 equals 3d. So -9 equals 3d, so d equals -3. So now we can write a general term an to be a1, which we know is 8, plus quantity n minus 1 times d, which is -3. So we get an, if we want to simplify it a little bit more, we get an equals 8 plus -3n, which just becomes -3n, and then -3 times -1 is just +3, so +3. And for an, we have, if we simplify, we get 11 minus 3n. Okay, so now that we have an, which is of course one of the things we were asked to find anyway, we can easily find a12, because a12, as we know, is going to be basically obtained by replacing n here with 12. So we get equals 11 minus 3 times 12. Okay? So we get a12 equals 11 minus 36. So a12 is going to be -25. Okay, so there's the other piece of information we were looking for, and that's how we would approach that one. Okay. The only other thing is to notice that this may be written as an equals -3n plus 11, and that's fine as well. They're basically the same result. Okay, let's go ahead and move on. All right, here we have an arithmetic sequence, which is a little bit more abstract because it's given in terms of another variable. No problem, same approach. We're given a1 is x and a2 is x plus 3. We want to find a6 and an. So given that we do have a pair of consecutive terms, we can easily find the common difference, right? And all we have to do is go a2 minus a1. Of course, we can just look at this and we know the common difference is going to be what? 3, because we take a1 and add 3 to get a2. But let's go ahead and verify it using our formula anyway. So we get x plus 3 for a2 minus x for a1, and we end up with that 3 as well. Okay, either way, just by reasoning or by applying the formula. And then we have the first term and the common difference, so we should be able to find the nth term expression very easily, which will then help us find any term that we want, right? So we'll go on with that. So we have an equals a1, which is x, plus a quantity n minus 1 times the common difference d, which is of course 3. So now we can multiply that out and simplify it, so we get x plus 3n minus 3. Now I can find any term that I want. So a6, for instance, is going to be, remember, every place you see n, you're going to replace it with 6 in this expression for an. So we get x plus 3 times 6 minus 3. So we end up with a6 is equal to x. Now that's 18 minus 3, so plus 15. And there is a6. All right, so we have an and we have a6 right here. Okay, that's all there is to that. For our next arithmetic sequence, we're not given either A1 or D, but we're given A4 and A6. So we do want to find A1. So let's go ahead and see how we would approach that. We are going to go ahead and use the AN formula, which we know AN equals A1 plus quantity n minus 1D. Notice I write these very often because I find that if I continuously write them, then they become very easy to remember as well. So I recommend that to you as well. All right, so I'm going to write an expression for A4 using this general term formula. So I get A4 equals A1 plus 4 minus 1, right? So 3D. And I'm going to write one for A6. So I get A6 is equal to A1 plus 6 minus 1 this time, which is 5D. Now, I know what A4 is. That's negative 11, right? So I get negative 11 is equal to A1 plus 3D. And we also know what A6 is, so we can replace that with negative 15. It's going to be A1 plus 5D. All right, so now we just have a simple system of two equations in two unknowns, which once solved will give us both A1 and D. Now, I can go ahead and just, subtract the equations, or I could multiply one by negative 1 and add, but there's no need for that. As long as you're careful, you can just subtract these two equations. So negative 11 minus negative 15, that becomes my negative 11 plus 15, so that's positive 4. Remember, we're subtracting. Now, A1 minus A1 will cancel out. So 3D minus 5D, that's going to be negative 2D, right? So that gives me D is equal to divide both sides by negative 2. So you get negative 2. So there's the value of D. And if I take that and let me get rid of that real quickly. If I take it and plug it into either one of these two equations, I'll get the value for A1. So I'll just go into the first one. So we have negative 11 equals A1 plus 3 times D, which is negative 2, right? So we get negative 11 equals A1 minus 6. So therefore, negative 11 plus 6 is going to be A1. So A1 is equal to negative 5. All right, so there it is. So we weren't asked to find D, but we basically ended up having to find it because we were gonna solve that system anyway. All right, so that's all there is to that one. You just have to sometimes do a little bit more work, but really, really not that difficult, right? Okay, so this may be a good time to pause and ask, why are arithmetic sequences named that way? What does arithmetic have to do with these sequences, right? In order to understand the reason for the word arithmetic in the name of arithmetic sequences, we need to recall the definition of the arithmetic mean of two real numbers. The arithmetic mean of two real numbers A and B is none other than the familiar average of the two numbers, which is given by, as you know, A plus B divided by 2. So the reason arithmetic sequences are so named is the fact that if you take any 3 consecutive terms in an arithmetic sequence, the middle term will be the arithmetic mean of the other 2. Now, you may go, why? Well, don't take my word for it. Let's prove it, okay? To see that, we're going to consider three general consecutive terms in an arithmetic sequence. I'm going to consider, well, an in the middle, then the one that comes before that will be what? An minus 1, and the one that comes after that, or the term that comes after that, will be the an plus first term, right? Now, we know that an itself is a plus quantity n minus 1d, right? So what would an minus 1 be? Well, it would be a plus, remember, you always want, in this parentheses here, in this group, you always want one less than the term number. So what's n minus 1 minus 1? That would be n minus 2, right? So that's why an minus 1 is going to be a plus quantity n minus 2d. And for the an plus first term, we're going to have a plus, what's going to go here? It's going to be 1 less than the term number. What's n plus 1 minus 1? Well, the ones cancel out. You just get what? N. So that's why the an plus first term is going to be a plus nd. So the average of an minus 1 and an plus 1, which is the same as the arithmetic mean of these two numbers, notice, is going to be the sum of this term right here, or this value, I mean, a plus quantity n minus 2d plus this value, a plus nd, and then we divide that by 2. So now if I just simplify this, I'm going to keep the a, I'm going to distribute the d, so I get plus nd minus 2d plus a plus nd over 2, right? So notice that here I'm going to end up with 2a, right? And 2nd, so 2a plus 2nd, and we already have that minus 2d there as well, right? And then all of that divided by 2. So notice they're all, these terms up here are divisible by 2, so we can simplify and just get a plus nd minus d. Now, if I just keep the a and factor out the d, I end up with quantity n minus 1 times d. But what is that? Notice that's an. So we took three consecutive terms, and we found that the middle one is the average of what? The other two. And that is the proof of why the claim we made up here that if you take any three consecutive terms in an arithmetic sequence, the middle one is going to be the arithmetic mean of the other two, and that is why these sequences are called arithmetic sequences. Now, if you look at a simple example like the one that we saw on the first screen, 2, 5, 8, 11, 14, etc., verify that. Just take any of three consecutive terms like these three, right? What's 8 plus 14? 22 divided by 2, which is what? 11. Take 2 and 8. What's 2 plus 8? 10. What's 10 divided by 2? 5. So you can see this in action with a simple sequence like that as well. All right? So that's why these sequences are called arithmetic sequences. All right, next we want to turn our discussion a bit visual and see what graphing an arithmetic sequence might look like. Now we can obtain a graph of an arithmetic sequence with replacing the usual x-axis with what we call the n-axis. And we also replace what we normally call the y-axis, the an-axis. In other words, we call the horizontal axis n and the vertical axis an instead of the usual y-axis or f of x axis, right? Now, if we take this equation that we have for the nth term, well, this formula really for the nth term, then if we just take it and expand it like this, we can write it as a1 plus dn minus d. And if I put the dn first and lump the a1 minus d, which are just two constants, together, notice this becomes the usual linear pattern that we're used to, with an playing the role of y in y equals mx plus b. The d here with the common difference playing the role of m in y equals mx plus b. The n again plays the role of x here, right? An played the role of y, and n itself plays the role of x in y equals mx plus b. And this difference here, that's just a constant, right? A1 is a constant, d is a constant, so their difference is a constant. That is what replaces the y coordinate of the y-intercept in the usual y equals mx plus b. So we can see that the equation of an arithmetic sequence can be written in a linear format, and the points representing the sequence on the what we call, instead of xy plane, the NaN plane should be collinear. The slope of the linear pattern is d, which is the common difference of the linear progression. So a very nice connection to between arithmetic sequences and linear functions. All right, so next we want to plot the linear progression given here in the Cartesian coordinate plane, where of course the horizontal axis will represent n and the vertical axis will represent an, by first finding an equation for the linear pattern. All right, well, that should be quite simple for us to do. Remember, these are the equations of interest, and this last one is the simplified version we're interested in, which is in our typical linear format. So we want to work with an equals dn plus quantity a1 minus d. Now, do notice that a1 is 2 and d is 5 minus 2, which is 3. So I end up with an equals d, which is 3 times n, plus quantity a1, which is 2, minus d, which is 3. So basically, I get an equals 3n minus 1. Okay, so if I make a quick table of values for n and an, you can see that, for example, when n is 1, I get 3 times 1, which is 3 minus 1, which is 2. If n is 2, I get 3 times 2, which is 6 minus 1, which is 5. If n is 3, we get 3 times 3 is 9 minus 1 is 8. If it's n is 4, I get 3 times 4 is 12 minus 1 is 11. 5 will give me 15 minus 1, which is 14. So, but then we just plot those points. And as expected, notice the pattern is linear and the points are what we call collinear. And that should always be true for any arithmetic sequence. So there is the equation for the linear pattern, and there is the graph of the linear progression. The partial graph, of course, this keeps going unless there is some kind of a restriction on, and there isn't one here. So this is just a part of the graph. The entire graph would just keep this collinear pattern going forever. All right, and of course, if you were to graph the corresponding y equals mxp version of this, you would have y equals 3x minus 1, right? And if we just quickly graph that, you'll see, one second. Okay, so here in red, you'll see just the graph of f of x equals 3x minus 1 or y equals 3x minus 1. It's a simple line, right, with a slope of 3. Notice to get from this point to this point, for example, you have to go up 3 over 1. So we know exactly what this looks like. The y-intercept is at 0, -1, right? So, but of course, for our linear progression, we only start with 1, n equals 1 for the input, and we're not going to have any of these parts in the middle of these, right? Our linear progression will not have the line, and it will only have those points in it, okay? So that's the relationship there between arithmetic sequences and linear patterns. All right, so this time we're given a graph of an arithmetic progression, and we're asked to find the formula for the nth term of the arithmetic sequence, and then state the domain and range. And this time we're told that this is a finite sequence. In other words, what you see is all there is. It doesn't keep going forever, okay? So we can just look at this graph and see, for example, 1, 1 is on this graph. So if I make a table of values, using n and an, I see I have 1, 1 on there, and then I notice that 2 is n equals 2 is paired up with 4 for an. 3 is paired up with 7, right? Etc. So my arithmetic sequence is the what you see on the right here. So 1, 4, 7, etc. Right? So it's easy to find a1. That's just 1, right? The first term of this sequence is 1. D is, of course, easy to find. You just do 4 minus 1, right? And now I should be able to write the formula for an, or the nth term, right? It's going to be dn plus a1 minus d. I can use this or I can use that. Makes no difference. So let me, since I'm working with these patterns, let me just use this. So dn, so 3n plus quantity a1, which is 1, minus d, which is 3, just like that. So we have an equals 3n minus 2. So there's the formula for the nth term of the finite arithmetic progression, and the domain and range. Let me just go ahead and continue with 4. If I plug in 4, I get 12 minus 2 is 10. And 5, so 15 minus 2, 13. And it's verified on the graph as well, right? So the domain, remember, is the set of all n values, right? Normally x values, but in this case, we're using n for the horizontal axes. So the n values in play are 1, 2, 3, 4, and 5. And the range is the set of all the outputs, or an values. So 1, 4, 7, 10, and 13. Remember, this is a finite arithmetic progression, and you're seeing all the terms depicted in this graph. Okay, so that's how you would approach that one. So here's an easy one. Can the plot given here be a representation of an arithmetic progression or an arithmetic sequence? Explain your answer. Of course, as you can see, these dots represented here are not collinear, so this cannot possibly be representing a what? A linear progression. All right, so that's an easy one. In our last lecture, after we learned about sequences in general, we learned about series in general, and in this video we're going to follow the same pattern, but we're going to talk about arithmetic series only. As was the case with a general sequence, the sum of the terms of an arithmetic sequence also create what's called an arithmetic series. We can develop a formula for the sum of the first n terms of an arithmetic sequence using a method similar to the one utilized by the young Carl Friedrich Gauss when his teacher asked him to find the sum of the first 100 numbers to keep the class busy, which was of course also the method that we used to find the formula for the sum from I equals 1 to n of I in our last video. So what we do is we let a1 plus d, a1 plus 2d, etc., all the way up to the nth term, a1 plus quantity n minus 1d, be the first n terms of an arithmetic sequence, okay? Then we can write the sum twice. Remember, Sn represents the sum of the first n terms of a sequence. Now, the sequence may just be finite and only have n terms, or it could have infinitely many terms. It makes no difference. But Sn represents a finite sum only from 1 to n. All right, so from the first term through the nth term. So we can get a1 plus a1d plus a1 plus 2d, etc. So this is a1, remember this is a2, this is a3, all the way up to a1 plus quantity n minus 1d, which is of course what? Remember, this up here is just an. Now, if I write it backward, in other words, I start with the last term, an, and then what's the next term before it going to be? Well, it's just going to be an minus d, right? And what's two terms before an? That's going to be an minus 2d. We're just reasoning backward, right? And all the way up to what? The first term, which is a1. So we're writing this same sum, but in a backward manner. So notice that then if I add these two equations, I end up with 2Sn on the left. On the right, what is that sum right there? That's a1 plus an. What's this sum? Well, remember, when you add these two, the d and the minus d will cancel out. Once again, you get what? You get a1 plus an. And these two, again, these two will cancel out. You get a1 plus an. So you basically end up with n of these sums of what? a1 plus an. So 2Sn is going to be n times a1 plus an. So all I got to do to get the expression for Sn is divide both sides by 2. So that's how you end up with the sum of the first n terms of an arithmetic sequence being n times a plus 1 plus, n times quantity a1 plus an over 2. Just like that. And we're going to be using that sum formula, so we're going to want to keep that in mind. And of course, it's very simple. It's n, which is the number up to which we want to add the terms of the sequence, times the first term plus the last term, and then divided by 2. And of course, not the last term of the sequence, but the last term up to which we want to add the terms. If it happens to be a finite sequence of only n terms, then yes, it'll be the last term. But if it's infinite and we only are considering the first n terms, then it's not the last term, but just the nth term. Now, we notice that since an is a1 plus quantity n minus 1 times d, we can also write the formula for Sn by replacing the an with a1 plus quantity n minus 1d. If we clean that up, we end up with Sn equals n times 2a1, see, plus n minus 1d. So here is another format for the sum of the first n terms of an arithmetic sequence. Basically, we will use this simpler version if we know both the first and the last terms, and we'll use this slightly more complex version if we only know A1 and D, but not the last term that up to which we want to add, okay? But of course, we do need the term number up to which we want to add the terms of the arithmetic sequence. All right, so for this example, we want to find the sum of the first 96 terms of this sequence given here. Now, this sequence, of course, keeps going because obviously it has at least 96 terms. So here we should go ahead and put comma and then an ellipsis to indicate that the pattern is continuing. All right, so what do we know? Well, we know A1, don't we? A1 is 43. Now, do we know D? Well, not yet, but it's very easy to find, right? Just 49 minus 43, for instance, right? So we know D now. Do we know N? Of course, because we want to find the sum of the first 96 terms. So N is 96. All right, so given that that's all that we have right now so far, the first term, D and N, which of these formulas would be better to use? Well, remember, we would use this one if we knew A96, but we don't, and rather than having to go first find that and then use this formula, we can just use this formula, which doesn't require us to know the 96th term at first. It will just be calculated implicitly within that formula. So we want S96, and we're using this formula. So we get 96 times 2A1, so 2 times 43, plus quantity 96 minus 1, which is 95, and then times D, which is 6. And then we take all of that and we divide it by 2. So all we just have to do at this point is to calculate that. Okay, so we have 96 times 2 times 43, that's just 86, plus 95 times 6, and then we're going to get out of the parentheses and divide all that by 2. So we get 31,488. So basically what that is, that's basically 43 plus not 49 plus 55 plus 61, and then keep going till what? Till the 96th term. And that's the sum we just found, okay? All right, so there we have it. Let's move on. Next, we want to find the sum of the first 1,000 positive integers. Now, if you think carefully about this, you should realize you already know how to do this because of the summation rule number 1 that we stated and proved in our last video. Let me remind you of that rule real quickly. So here it is. Notice we can just do the sum from I equals 1 to 1,000 of I, and we can then use this formula to find it. But it's interesting to see that these two formulas will actually become the same when dealing with this particular type of problem, because notice that this is also the sum of the terms of an arithmetic sequence, because what are the first 1000 positive integers? But as a sequence, they will look like this. 1, 2, 3, 4, right? All the way up to what? To 1000. So my first term is 1. And what is the common difference? Well, these are just consecutive positive integers, right? So 2 minus 1 is going to be the common difference, which is 1. All right, and what is the nth term or the thousandth term? Where this is as simple as it gets, right? It's just going to be 1000. So I have a 1000 as well. And that happens to be 1000. So I can find S 1000. And that's going to be, we can use this formula because we know both A1 and AN. And of course we know N. N is 1000 times the first one term of this sequence is 1. And the nth term is 1000, right? And we divide that by 2, so we can quickly compute that. So we have 1000 times 1001, and we need to divide that by 2. So we get 500,500. Now notice that you could have used this formula in this manner. You could have done the sum from I equals 1 to 1000 of I from our last lecture, which would have been the same series. It would have been the series consisting of 1 plus 2 plus 3 plus ... all the way to 1000, right? And it would just be 1000 times n plus 1, which is 1001 over 2. So no inconsistency here. We could have done it using techniques from our previous lecture as well. But it's nice to see that it works with our new formula as well. All right, so the main thing is to recognize it in this particular lecture as an arithmetic sequence, and therefore S1000 being the sum of the first 1000 terms of that arithmetic sequence, with the first term being 1, the 1000th term being 1000, and the common difference being 1. All right, so make sure you understand that and we'll proceed. All right, here's another one. We want to find the sum of the first 16 terms for an arithmetic sequence with A2 equal 1 and A4 equals 3. See if you can figure that out. You should be able to, and then come back and see if our answers agree. All right, so remember we have two options that, you know, as far as formulas we can use. So we have to see which one fits our purposes better. Now, we don't have A1, we don't have AN, which is A16 in this case, right? We don't even have D, right? But of course, we can figure out A1 and D in the same way that we calculated it before in a similar scenario. We'll start with the formula for the nth term, right? We know that AN for this arithmetic sequence that we're finding the sum of the first 16 terms of is going to be A1 plus quantity n minus 1 D. So I know what A2 is. So A2 is going to be A1 plus, instead of n, I'm using 2. So 2 minus 1, that's 1 times D. So just D, right? Because 1 times D is D. And I know what A4 is. That's going to be A1 plus quantity 4 minus 1, which is 3d. Now I'm going to substitute 1 for a2, so I get 1 equals a1 plus d, and a4 is 3, so in this equation I'm going to replace a4 with 3. So there we have a system of two equations and two unknowns. We can easily solve it. Let's go ahead and subtract again. 1 minus 3 is negative 2. a1 minus a1 cancels out. d minus 3d is negative 2d. So divide both sides by negative 2, you get d equals 1, right? So let's go ahead and plug that 1 for d in the first equation here. So we get 1 equals a1 plus d. So 1 equals a1 plus 1. So that means a1 is equal to 0, 1 minus 1, right? So we have the first term now. We have the common difference, d, and we know what term we want, right? We want to add the first 16 terms. So we're interested in S16. And given that I don't know what the 16th term is, instead of using this formula, I'm going to use this formula because I know n, which is 16, I know a1, which is 0, and I know d, which is 1. So I get n, which is 16, times 2 times a1, which is 0, plus quantity n, which is 16 minus 1, so that's going to be 15, times d, which is 1, and then we have to divide all that by 2. So we end up with 16 times, that's just 0, right? And that's 15 times 1 is just 15. So you get 15 basically, right? And then over 2. So that's basically 8 times 15, right? So which is 80 and 40, right? So 120. And that's the sum of the first 16 terms of the sequence with a2 equals 1 and a4 equals 3. Next, we want to make another connection because between what we have learned in this lecture and something that we learned in the previous lecture, basically the idea of the summation. We noticed that if you have a summation and the summed, that's what we call the term that's being added repeatedly, or the sum term, you know, but summed is the nicer term for it. Then as it turns out, this is actually going to turn into the sum of the terms of an arithmetic sequence, with the first term, of course, being a1 equals d times 1. Remember, replace the I with the first term of the index, plus c, which is d plus c, and the common difference will be d. Because think about it, what would the second term be, right? For instance, a2 would be d times 2 plus c, right? Which is basically 2d plus c. And if this is a2 and that's a1, you know that the common difference is going to be a2 minus a1, which is going to be 2d plus c minus quantity d plus c, right? So it's going to be 2d plus c minus d minus c. which is, notice the c's cancel out, so you just get d, because 2d minus d is d. So that's how we know if we have a sum of this type, with the summand being of the form d times the summation index plus some constant, with d and c both being constant, then we're looking at an arithmetic sequence in disguise, right? The terms of an arithmetic sequence, I should say. And the sum also being the sum of the first n terms of an arithmetic sequence, therefore being an arithmetic series. Okay, so let's go ahead and use that fact. All right, so if we're trying to find this sum in this example, notice that it is going to be just the sum of the first three terms of an arithmetic sequence, with A1 being what happens when we run the first value of this summation. So we get 3 times 1 plus 4. Not there, the parenthesis goes here. 3 times 1 plus 4, so we end up with 7. And remember, this is of the form di plus c, and we decided that this would be the common difference, right? So d is going to be 3. So we don't really need to calculate what the third term is, because we can just use this version, right? So we get S3, which is, by the way, exactly what this is going to be n, which is 3 times 2 times A1, so 2 times 7, plus n minus 1. Remember, n is 3. So 3 minus 1 is 2. So we get 2 times the common difference, which is 3. From here, remember, that's going to be the coefficient of the I term here. And then over 2. Now we just need to compute that. So we have 3 times, that's 14 plus 6, so 20. And then divided by, we need to get out of the parentheses, and divide that by 2. So we have 30 for that sum, okay? And that's how you do that one. Now, it is important for you to realize that we could have used, again, the techniques we learned in our last class, which was to take the sum from I equals 1 to 3 of 3i plus 4. Break it up. You could always break it up. Wrong place. Okay. Quantity 3i plus 4. So notice we can break that up as the sum from I equals 1 to 3 of 3i plus the sum from I equals 1 to 3 of 4, and apply some of the rules and formulas we learned from last time. Here, for example, I could bring the 3 out, plus the sum from I equals 1 to 3 of 4. Now, I do want you to work these out using the techniques from the last class and verify that you end up with 30 as well. So more than one way to handle these problems, but this is always a nice fact to see connections between concepts in math. That's how you gain mathematical depth, okay? All right, so that's that. All right, so here we have another one. It looks like very similar, right? But there's something you have to be extremely careful about. This sum is not running from I equals 1 to 12. It's running from I equals 4 to 12. So that's going to change matters a bit. So, but there is a clever way you can deal with that. What we'll do is realize this, that the sum from I equals 4 to 12 of, I'm going to write that as negative 6I minus 5, and you'll find out in a minute why, is going to be, now the sum from 4 to 12 of this expression can be found by taking the sum from 1 to 12 and then subtracting from that the sum from 1 to 3, right? So the sum of the first three terms of the corresponding sequence. So that's how we're going to handle it. So we're going to say that's equal to the sum from I equals 1 to 12 of negative 6I minus 5 minus the sum from I equals 1 to 3 of negative 6I minus 5. So in other words, think about it this way. You have A1 plus A2 plus A3 plus A4 plus A5 plus all the way up to what? A12, right? So what we're saying is, if you take the sum of those 12 terms, right, and take away from it A1 plus A2 plus A3, this sum, right? So this is S12 and this is S3, right? Now, if you take S12 and subtract from that S3, what do you end up with? You end up with this. What is that? That's the sum from I equals 4 to 12 of the expression we're interested in. So that's how the logic works, okay? So now all we need to do is we need to know what, well, obviously for this one, for instance, we know n is 12, right? We need to know A1, which is, remember, just run the value of 1 through the expression. So negative 6 times 1 minus 5, so that's going to be negative 11. And we need to know the common difference, of course. Remember, that's why I wrote it in this format, because in this format, I know that the coefficient of I is going to be the common difference, so negative 6. And now we're ready to go ahead and compute. So we're going to use this formula. So for n equals 12, I get 12 times 2 times A1, which is negative 11, plus quantity 12 minus 1, that's 11d. So 11 times negative 6 over 2. So that gives me the sum from I equals 1 to 12 of that expression. I need to subtract from that, not equals, I mean minus. Now I'm using n equals 3, so 3 times 2 times A1, so 2 times negative 11, plus 3 minus 1 is 2, so 2 times the common difference, which is negative 6. And then we divide that by 2 as well. So we handle that subtraction and we will be done. All right, so we have 12 times, that's negative 22 minus 66. And then we need to get out of the parentheses and divide that by 2. Now we need to get out of the fraction and say minus 3 times, now that's going to be negative 22 minus 12. Then we need to get out of the parentheses and hit divided by 2. Finally enter, so we get negative 477 for that particular problem. All right, so remember, always be aware that that initial index should be 1 for the techniques we've been discussing to work. So if it's not, you have to figure out something clever like we did here in order to be able to use the same techniques, okay? And that is all there is to this one. Okay, so make sure you can handle that. A little bit different, a little bit trickier, but not super difficult, okay? And we'll go on to a couple more problems, and that should do it for the day. All right, here's another problem. Go ahead and see if you can figure this one out. We want to know the A1, the first term, and the common difference for an arithmetic sequence whose 12th term is -18, and the sum of the first 12 terms is -107. Pause the video, see if you can figure that out. I think you will if you give it enough of your time. So try it and then come back. All right, so I can see that this is a formula that involves Sn as well as An. And if I use this formula, given that I know n here is 12, I should be able to get A1, right? So let's try that. So we have S12 is equal to n, which is 12, times A1 plus An. I don't know A1, so I'm going to keep it as A1 plus An, which is A12, over 2. Now let's substitute. We know that S12 is -107, and we keep A1 as A1, and we know that A12 is -18. So plus -18 is just -18 over 2. So now if I cross multiply, I end up with 12 times A1 minus 18 equals 2 times -107. So 12A1 minus, we need to know what 12 times 18 is. So 12 times 18, 216, so minus 216 is equal to 2 times -107, that should be -214, right? So we end up with 12A1 equals -214 plus 216. So 12A1 equals 2, and A1 is going to be 2 over 12, which is 1 over 6. Okay, so we know A1 now. That's 1/6. So now we have options. We can either use this formula here to get D, but it'll be much simpler if we just use our regular An formula, given that we know A12 and we know A1 and we know N. So that's what we'll do. So A12 we know is going to be A1 plus 12 minus 1, which is 11, D, right? Now let's plug in what we know. A12 is -18. A1 we found is 1/6, right? And D is the unknown, so we keep the D, so plus 11D. Now we just multiply both sides by 6 to clear the fractions. So we need to know 6 times -18. So we'll just do 6 times 18 and we'll make it negative. So -108. Remember, we're multiplying both sides of this equation by 6. So we get -108 is equal to 6 times 1, 6 just gives me 1. and 6 times 11d gives us 66d, right? So we have 66d is equal to negative 108 minus 1, which is negative 109. So we get d is equal to negative 109 over 66. Now, if you can reduce that, you should always do so, but I don't see 2 doesn't go into either one, 3 doesn't go. I believe these two numbers are relatively prime, so we can just leave it at that. All right, so there it is. Now there is a way to actually make sure, if you like, using this calculator that we've been using, so it's kind of handy. Let me show you. So you would type 109 over 66 and hit enter. It's going to give you a decimal answer. Now if you hit the conversion to back to fraction formula, if it were reducible, it would have given you the reduced version. Okay, so for example, if you do 14 over 6, we know that's reducible to 7 over 2, right? So if you do 14 divided by 6, it'll give you the decimal, but when you go back to fractional form, see, it'll give you the reduced format, which is 7 over 3. All right, so that's handy to know in case you ever have to use it. All right, let's go ahead and move on. All right, here's another one you should definitely be able to do. I recommend you take a pause and try it before you come back. Find the sum of the first 120 positive odd integers. Now, I think you will recognize this as the sum of the members of an arithmetic sequence, right? What does it look like? Well, here's the sequence: 1, 3, 5, 7, etc., right? So A1 is 1. Common difference is 3 minus 1, for example, or 5 minus 3, whatever. It's 2, right? So we're interested in the 120th member of this group, right? So we need to know what that is. So can we find it? Of course, because A120 is going to be A1 plus quantity n minus 1d, right? So it's going to be A1 plus 120 minus 1, which is 119, times the common difference, which is 2. So A120 is going to be A1, which is just, let's just replace that with 1. So 1 plus 119 times 2. 1 plus 119 times 2. So 239 is the 120th odd number starting with 1, right? So now it's easy, right? Because now we want basically S120 for this sequence. That means what? That means we're going to find out what 1 plus 3 plus dot 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 plus 237 plus 239 is going to be. And of course we can do that using this formula now, because we know A1 is 1, we know AN it's 239, and we know N, which is what? 120. So we get 120 times 1 plus A120, which is 239, and all of that divided by 2. That should give us the sum of the first 120 positive odd integers. All right, so 120 times, that's going to be 240, right? 1 plus 239, and then divided by 2. So we get 14,400. There it is. So that's the sum of the first 120 positive odd integers, or you could say natural odd integers, and odd natural numbers is what I mean. All right, so the first 120 odd natural numbers, or odd positive integers. All right, that's how you would do that one. Okay, finally, we want to look at two applications, and that's it. Honestly, this time, that's it for the day. All right, so here's an interesting problem. If a clock makes the proper number of chimes each hour on the hour, how many times will it chime in 30 days? Now, we know that basically when it's, for example, 1 o'clock, it's going to make 1, and then when it's 2, it's going to make 2 chimes, and then 3, right? But not all the way up to 24, right? It's going to do that all the way up to 12. And then when it's 1 o'clock again, it's going to do another 1 chime. So basically, we do want the sum from 1 to 12 of the terms of this sequence. However, in order to count for the fact that this is going to happen twice every day, we're going to multiply that by 2. So we want the sum 2 times S12 for this for the terms of this sequence, and then of course we need to multiply that by what? By 30. So basically we're going to have 2 times, now we're going to use this formula, right? The sum of the first 12 terms of that sequence. Now, we do have to find what A12 would be, but remember, that's easy with this problem because it's just going to be the 12th element, which is right there. It's 12, right? This is a really nice, simple problem when it comes to finding these quantities. So, and the A1 is just obviously 1, right? So, and the number of items is 12. So, 12 times 1 plus 12 over 2. And then we're going to multiply that by 30. Okay, so obviously we don't need to worry about these two because they cancel out. So basically we're looking at 12 times 13. 1 plus 12 is 13 times 30. So basically 4,680 chimes in 30 days. Okay, and that's how you would do that one. All right, then here's our last problem for the day. Go ahead and see if you can figure it out before you watch the rest. How much material would be needed for the rungs of a 40-rung ladder if the rungs taper uniformly from 20 inches to 50 inches? Okay, so is this what you did? So I'm looking at a ladder, so it has rungs that are getting increasingly larger, right? And basically we know that it's happening uniformly, so that's why an arithmetic sequence would make sense here. And the kind of sequence that we're looking at, whose sum of whose terms would be interested in, would look something like this, right? The first term would be 20, right? And then the last term would be 50. And of course, this is going to be A1, and the last term is going to be the 40th one, right? Because it's a 40-rung ladder, right? And N, of course, is going to be 40. And that's all we need to know. So the sum of these lengths, right, is just going to be the sum of the first 40 terms of this sequence, or all the terms of that sequence. It's a finite sequence, right? So Sn is going to be n, we're using this formula, 40 times a1, which is 20, an, which is 50, and then over 2. So we can compute that, and that's it. So we have 40 times, that's 70, 20 plus 50, and then divided by 2. So we end up with 1400 inches. So you would need 1400 inches of material to be able to build a ladder like that. And that pretty much brings us to the end of this lecture. So I hope you learned much, and take care until our next one.